So we're going to try and solve a simple Doppler effect problem. A motorcycle is travelling past, it's travelling at 45 metres per second, and it sounds the horn, and the horn sounds at 250 hertz. They're passing a stationary observer. We're going to look for the apparent frequency as they approach and as they recede. So let's take a look at what we've got in this equation here. So we're going to write down what we know about our situation, and we're going to write down the formula that we're going to use. Now we know the frequency, the actual frequency of the sound, the frequency that the rider will hear is 250 hertz. We know that the motorcycle, the source of the sound, is travelling at 45 metres per second, and we know the velocity of sound in air is 330 metres per second. We also know the formula that we're going to use. The tricky bit, the thing that we're going to need to work out, is when we use plus and when we use minus. So if you find that hard to remember, I suggest in your exam or when you're doing any kind of test that you draw yourself a quick little picture of a source, a point source, and you draw the Doppler effect happening around it. Okay, and you remember that, sorry, it's a bit wiggly, but you remember that as you're approaching, yeah, it's going to be minus, okay, it seems counterintuitive, and as you're leaving, it's going to be plus, okay, and you can just remember that, okay, you can work it out from first principles if you prefer, but remembering it is going to probably be easier. As you're approaching, you make a minus so that you make this line here, the bottom line, you make that smaller, therefore making this whole fraction greater than 1. As you're receding away, you plus it, making this line here bigger, making this whole fraction, this whole multiplier, less than 1. Okay, therefore changing the apparent frequency. Anyway, when we do some maths, okay, as we're approaching the person, it's going to be 250 times by 330 over 330 minus 45, which is going to be, what, 285, 95. Anyway, it's going to be some number that's smaller than 330. And when you calculate that in your calculator, that works out to be 290 hertz, which is what you'd expect, a higher frequency. This is where you can be like, oh yeah, did I actually do that the right way around? If you're approaching and your f dash is smaller than 250, like a lower frequency than 250, you know that you got your plus and minus sign the wrong way around. Yeah, better go and fix that. So we'll do exactly the same thing, yeah, but this time when you're receding, it's going to be a plus, and the answer works out to be 220 hertz. Now, in your actual assessment, if this was an actual exam question, I would put in brackets next to it receding, and the other one I would put approaching, just for myself. Now, a common corollary or follow-up question to this you'll hear is, why does the stationary observer hear 250 hertz just as the motorcycle is passing them, or when the motorcycle is directly opposite them, or some words to that effect? It's basically saying, why do you not hear the Doppler effect as the motorcycle is exactly, as the source is exactly opposite the person? So to think about that, here's your source and here's your person. So for that instant, as your person is directly opposite your source, okay, even though the Doppler effect is going on, at that point there, yeah, when the person is directly opposite the source, there is no relative movement or relative velocity difference between the source and the person. Therefore, the person will observe 250 hertz. So the key things that you need to talk about are at this instant. Okay, so you're making it clear that you understand that this is an instantaneous event. the horn is not approaching or receding relative to the observer. Okay, so you've made it clear that there is no relative motion between the horn and the observer at that point. Therefore, they will observe 250 hertz, or they will hear a 250 hertz horn, because there is no Doppler effect in action at that moment, and they will hear the same as the rider would hear. So that's a really common follow-up question. Why do you hear this? And it's got a relatively simple answer. The key thing is the horn is not approaching or receding at that instant relative to the observer.